Welcome to electrodynamics class. First of all, we deal with electric displacement vector D. It is defined as amount of charge displaced through unit area. That is, charge, if Q is the charge, then the total area of a spherical shell is 4 pi r square, then electric displacement D equal to Q by 4 pi r square. Here, the displacement, you just follow this figure for understanding what is meant by displacement of charge. Here, this is a spherical shell, and a plus Q charge is placed at the center of the shell. So, by induction, on the inner side of the spherical shell, negative charges are induced, and on the outer side, the positive charges are introduced. So, this positive charge at the center is displaced through a distance r to the outer surface of the spherical shell. That is why we are calling it as electric displacement. And the electric intensity E on the surface, E equal to 1 by 4 pi epsilon 0 Q by r square into unit vector r that we have studied in the previous chapter. So this can be rearranged as Q by 4 pi r square into 1 by epsilon 0 into unit vector r. So what is this Q by 4 pi epsilon 0? Sorry. What is this Q by 4 pi r square? Q by 4 pi r square is D. So substituting for Q by 4 pi r square as D, this equation becomes D vector D equal to epsilon 0 E. The integral form of Gauss's law can be stated as surface integral E dot dA is equal to 1 by epsilon 0 Q enclosed. So now we have to find the integral form of Gauss's law in terms of the displacement vector D. So this can be written as, we bring this epsilon 0 to LHS, this can be written as closed surface integral epsilon 0 E dot dA is equal to Q enclosed. So what is this? Epsilon 0 E, this is equal to D. So this equation becomes surface integral D dot dA equal to Q enclosed. So this is the integral form of Gauss's law in terms of D. So that is correct. Now let us find the differential form of Gauss's law in terms of D. So for that, first of all, we are taking this equation here, that is surface integral D dot dA is equal to Q enclosed. So what is Q enclosed? Q enclosed means the enclosed charge within the Gaussian surface. So that is equal to the integral, volume integral of the charge. We know the volume charge density rho is equal to charge by volume. That is rho equal to charge is Q enclosed by volume is D2. Charge dq, volume is d2. So we can write rho equal to dq by d2. So what is dq? dq becomes rho d2. So instead of dq, we are writing rho d2. So for this q enclosed, we are substituting this integral, volume integral rho d2. And at the same time, we are applying Gauss's divergence theorem to the LHS of this equation. This is the LHS part. Here we are applying the Gauss's divergence theorem. So what is Gauss's divergence theorem? The surface integral can be converted into volume integral, just like this. So if you convert this surface integral into volume integral by using Gauss's divergence theorem, you are getting closed surface integral D dot dA is equal to volume integral del dot D d2. And so considering this point in the LHS of equation number 1 and substituting for Q enclosed, you are getting the equation just like this. So instead of this, we are writing this one, correct? Then instead of this, we are writing this one. So you are getting closed surface, closed volume integral del dot D d2 is equal to volume integral rho d2. And what happens? d2, then you are getting del dot D equal to rho. So this represents the differential form of Gauss's law in terms of vector D. Now let us discuss about the Gauss's law in presence of dielectrics. What is the change of Gauss's law in the presence of dielectric? At first, you just imagine what is meant by a dielectric. Dielectric is an insulator, but all insulators are not dielectrics. The insulators which show the property of polarization is called dielectric. All insulators are not dielectrics, but all dielectrics are insulators. Insulators which show the property of dielectric polarization. And a dielectric is placed in an electric field. In an electric field, dielectric is placed. That is, if you consider the case of the capacitor, two plates, you just imagine the positive plate and negative plate. Inside the plate, within the plates, we are filling with the dielectrics. Then it becomes a capacitor. So, in between positive and negative plates, a uniform electric field is produced. So, you imagine such a situation here also. Dielectric is placed in electric field. So, what happens to dielectric? The dielectric in between the metal plates, that is in a particular electric field, is get polarized. What do you mean by that? The positive charges move towards one side and negative charges moves towards the other side. So there arises a net field. First field is the applied field, and this applied field is due to the due to the presence of free charges. And second one is the field caused by polarization due to bound charges. What are bound charges? Bound charges, the charges accumulated due to polarization is called bound charges. And considering this bound charge, we can define the surface bound charge density sigma is equal to sigma b, bound charge density, P dot n, and the bound charge volume density rho b is equal to minus del dot p, where this capital P is dielectric polarization vector. So now let us imagine what is the differential form of Gauss's law we have studied in the previous chapter. That is, del dot E is equal to rho by epsilon 0, but rho is a combination of these two, that is the free charge rho f and bound charge rho b. So substituting for rho, that is substituting 2 in 1, you are getting del dot E is equal to rho f plus rho b by epsilon 0. And bring this epsilon 0 into LHS, you are getting del dot epsilon 0 E equal to rho f plus rho b, where rho b is equal to minus del dot p, where p is the dielectric polarization. Substituting for rho b, that is the bound volume charge density, we get del dot epsilon 0 E equal to rho f minus del dot p. Bring this del dot p minus del dot p to LHS. So this equation becomes in this form, and you take this equation as del dot within the bracket, you put epsilon 0 E plus p as common factor, and this is equal to rho f. And here this term, the epsilon 0 E plus p, is defined as d, electric displacement. So electric displacement is denoted by the equation d equal to epsilon 0 E plus p, where p is the dielectric polarization. And this is equation 4 and this is equation 5, and from 4 and 5 we get the equation del dot d equal to rho f, del dot d equal to rho f. So this is the differential form of Gauss's law, But if you remember, without dielectric, the same equation is del dot d is equal to rho. And here the d, electric displacement vector d, is caused by free charge distribution, entirely due to free charge distribution. Okay, thank you. Now we We are deriving the integral form of Gauss's law in the case of a dielectric. So we have this relation del dot D equal to rho F. For an elemental volume D2, for a small elemental volume D2, this expression can be rewritten as del dot D D2 is equal to rho F D2. And for the complete volume tau, this is integrated. So integral del dot D D2 is equal to integral volume integral rho F D2. And this is equal to QF, because Q is equal to rho into volume. So QF is the total free charge in volume tau. So by using Gauss's divergence theorem to the LHS of this equation, this LHS becomes closed surface integral D dot D. And by using equation 1 and 2, we can rewritten as surface integral D dot dA is equal to QF, which is the integral form of Gauss's law for a dielectric. Now we have to prove del cross D equal to del cross P. What is D? Electric displacement vector. What is P? The dielectric polarization vector. So for this, you just first of all you just assume this equation D equal to epsilon 0 E plus P. So where E is the total field and P is the polarization vector, epsilon 0 permittivity of free space, D electric displacement. And take curl on both sides. Here it becomes a del cross D, and here it becomes epsilon 0 into del cross E plus del cross P, equation 2. Electric field is irrotational. That is, the electric field cannot be curled. It is diverging. So del cross E is equal to 0. So put this del cross E is equal to 0. This becomes 0. So what happens? Substituting in 2, you are getting del cross D equal to del cross D equal to del cross P. So we are getting the result. For a uniformly polarized dielectric medium, these two equations are also correct. That is, del cross P is equal to 0 and del cross D equal to 0. You just remember these two equations also.